Well, thank you, Jean-Pierre. It's a pleasure to be here in person. This very exciting mission meeting, looking at the future of not only flying machines, but much more broadly the exploration of space. So I want to start off with sort of a summary of my message here today. I'm going to look at the history of flight in the solar system, and I'm going to look at the future. Venus was the site of the very first sustained flight of a vehicle beyond Earth. And this was by two Vega balloons launched by the Soviet Union in 1985. Now, since that time, there have been many proposals for balloon missions to Mars, Titan, and Venus. None have been selected so far. In my view, at this time, the prospects for balloon missions to Mars and Titan have faded, as more capable orbiters and rovercraft, which you just heard about, have occupied a significant part of what I'd call the scientific niche that lighter-than-air vehicles might have filled. For Venus, on the other hand, buoyant vehicles represent the prospect of rich scientific returns, which are not accessible to either orbiters, probes, rotorcraft, or landers, as you'll find out. So just a view for those of you who are not familiar with our companion worlds. Size-wise, Venus, cloud-shrouded Venus, is almost as big as the Earth. Mars and Titan are very much smaller. Of course, of particular interest to flight is what the atmospheres look like. And I don't want to go into detail on this chart of the comparisons, which shows the Earth at the surface at 35 kilometers, and Venus at its surface at 52 kilometers. Mars, as you know, has a very thin atmosphere, comparable to the Earth's at 35 kilometers in the stratosphere. Venus, on the other hand, the surface is very hot, 460 C, 90 bars. But if you go up to around 52 kilometers, the density of the atmosphere is about what it is in this room. And so you have the prospect here of testing vehicles for both Mars and Venus at conditions that we find accessible to us on the Earth. A little bit of detail on this very remarkable first flight of a vehicle in the solar system, the Vega mission. These vehicles were extraordinarily small. This was 40 years ago, remember. The balloon, 3.4 meters in diameter, suspending a total gondola mass of 6 kilograms. That 6 kilograms included 5 separate instruments, at least 5 distinct measurements. In 47 hours or so, each of these flew 1/3 of the way around Venus in the prevailing winds. They flew at a constant altitude because this was a superpressure configuration. So as the balloon went up and down, there was a restoring force that kept it around 53 kilometers. And they were communicated with from the ground. So this very small vehicle with a 1 kilogram battery communicated and sent data down to the ground for a period of 48 hours, and a global network of antennas communicated with it. So this was very much of a demonstration of what was possible at Venus, and something that we've been anxious to replicate since, but so far, yet it hasn't happened. So what did happen subsequently in the decade of 1990 to 2010? So here I'm really looking at efforts in Europe. So about a decade after Vega, there was an effort in concert with Russia by that time, because the Soviet Union had become Russia, and Kness was involved in the development of a Mars balloon. Now, unlike the Vega balloon, which was a super pressure balloon, this was zero pressure, which meant that during the nighttime, buoyancy was lost and the balloon sank back towards the ground. But it was restrained from hitting the ground by a snake-like tether, which removed and enabled the buoyancy of the balloon to keep the vehicle aloft. There were risks attached to this kind of concept, and maybe minimal science return, and for a variety of reasons that was canceled. Never happened. European attention then moved to Venus for something that looked more like Vega. And the European Venus Explorer, EVE for short, was a concept which was proposed to the ESA M3 mission in 2010, not selected for flight. After that experience, the European science community got together and looked at their aspirations for a future Venus mission. And they realized that their orbital mission was competing with this balloon mission, and they agreed to join forces behind an orbital mission. A wise decision. Envision was selected a year or two ago, and Europeans go on Venus with this very capable mission, but balloon missions, balloon aspirations were deferred. And then finally at Titan, as NASA and ESA worked together on a post-Cassini mission. In the planning for this, I first got to know Jean-Pierre very closely because we were both involved in this planning effort. And there were two concepts that competed. One to go to the Saturn system and one to go to the Jupiter system. And the Saturn system mission included a Montgolfier balloon that used the waste heat from the RTG to inflate the balloon and heat the gas inside it, so you didn't need to take helium there. The competition resulted in these two finalists, the Titan mission and a mission to Jupiter. Well, you all know the answer. JUICE emerged as the successful mission. The Montgolfier mission never happened. So let me go into a little more detail about some of the technical developments. I'm mostly familiar with those on the US side, although comparable things were going on in Europe. First of all, for Mars, although the Mars 94 mission was not super pressure, I'm sorry, I'm at Venus here. There was a Venus development at NASA. This is a super pressure balloon designed with a metallic film to maintain the temperature of the balloon during day and night, and protecting the balloon was a thin film of Teflon around the outside from the sulfuric acid. And so this was a concept that was pursued for two separate discovery missions called Vala and Ella and Viva. None were selected. There were, however, deployment and inflation tests that demonstrated the feasibility of aerial deployment and inflation. At Mars, the same concept of a superpressure balloon was developed for Mars. This was a much flimsier balloon because of the very thin atmosphere. You had to have a very thin membrane to float at those altitudes. Nevertheless, there were successful stratospheric tests of deployment, so something like this could, in principle, have worked. And then at Titan, there was work on this Montgolfier concept. On the left is a model that was tested at cryogenic temperatures to show, indeed, that you could heat the gas inside sufficiently to float, modeling results that demonstrated the same thing. Helium balloon tests that showed that on Titan, because it's so cold, helium diffuses very slowly, so a helium balloon would last for 10 years. And then there were also blimp-like concepts that had directional capabilities. So these were the kind of developments that happened in this period, out to about 2012. In 2014, we began to take a look at what the future really held. And I was involved in organizing a special session at our annual International Planetary Probe Workshop that year was held in Pasadena on the topic of sustained flight at Mars, Venus, and Titan. And it was very clear from that meeting that rotorcraft were emerging as an attractive solution for low-altitude imaging and surface sampling. And you've just seen how that can work from the presentations by Teddy and Ralph. Of course, these rotorcraft require recharging on the surface of the planet. They're inherently short range. The Mars vehicles are maybe 1 kilometer. The Titan vehicle, 10, maybe the prospect for further, but they're flights of comparatively short range, but playing a very important role for the next phase of exploration. Buoyant vehicles, in my view, still retain a role for regional and global scale. And as I mentioned, the environment of Titan enables very long-lived helium balloons because of low diffusion rates. At Venus, buoyant vehicles retain their importance in Venus exploration because you simply can't go to the surface and recharge your batteries for a rotorcraft. However, it became clear that constant altitude balloons were too limited in their science potential, so we needed to look at other kinds of capabilities. So about 4 years later, in 2018, NASA organized a couple of workshops to look at what the future held for Venus aerial exploration. And a number of different concepts were explored, some of them illustrated here, ranging from fixed altitude balloons to vehicles that had mobility in all three dimensions. And what clearly emerged from that assessment was that there was a sweet spot in future exploration, at least if you're looking for the next decade or so, between science return, complexity, and technology maturity. And that sweet spot was the variable altitude balloon. It couldn't move in all three dimensions, but it could control altitude. And two of the concepts for that, a so-called pump compression balloon, which is like a super pressure balloon inside a zero pressure balloon, exchanging gas between the two, and a mechanical compression balloon, a series of lobes whose volume can be changed by a tether connecting the upper and lower pole pieces. So these concepts were seen as applicable to operating in the same general region of the atmosphere that Vega had operated in. The middle cloud region would be for the pump compression balloon on the left side, on the center. And the mechanical compression balloon, we felt, could access the region below the clouds, which would be very important for future scientific potential. So this is a picture of a test that was conducted, a launch of a half-scale balloon. The full-scale balloon here would carry 100 kilograms, about 20 times what Vega had carried. And this balloon, as you can see from the peanut shape, there's a super pressure balloon in the lower part, and then the zero pressure balloon fills the main body of the vehicle. And this test was conducted in the Black Rock Desert in Nevada, USA, a very large expanse that allowed us to demonstrate this in a flight over around 20 kilometers, went up to a few kilometers altitude, and demonstrated this altitude change capability. This was going to be a video. Let's see if it works. So here are the people getting the balloon inflated, flew for the first time. Subscale, as I mentioned. And the intent here is that this would fly for about 100 days at Venus. And again, this, like the earlier superpressure balloon, is protected against the sulfuric acid with an external film of Teflon. And here it goes. There were actually 2 successful flights on successive days, demonstrating the success of this particular technology. And pumping gas from the zero pressure balloon back into the super pressure balloon brings it down, or simply releasing gas into the other chamber allows the balloon to rise. So we see this paving the way for a long-lived balloon mission, initially a target of 100 days, and in the future, much longer. And JPL was involved with this, as well as the Near Space Corporation. I'm trying to advance this to the, here we go. So what will this balloon do? So here I'm going to review the range of science that we're envisaging for this particular concept. The first thing is that this balloon is going to be flying in the clouds. It's going to have an altitude range of 10 kilometers. So for the very first time, you're going to be able to investigate the actual chemistry of the cloud particles in situ and their astrobiology. Some believe that life may exist in the clouds. A much broader community thinks it's important to understand what the chemistry is, to understand the potential for habitability in the clouds. And to do this in situ, people have attempted to do this remotely for decades and are no closer today than they were maybe 20 years ago. So that's one step. The next step is to understand the atmospheric dynamics. What drives the circulation of Venus? And much we can learn about this from an orbital view, but be there in situ, measuring the velocity at one particular place accurately, and the upward and downward radiation is critical too. But what we can do with this isn't limited to understand the atmosphere in the region we're flying. We have the potential for doing revolutionarily new geophysical measurements, taking advantage of this location. And two classes of these are shown here. The upper box shows the measurement of infrasound, which is sound generated by seismic events or volcanic eruptions take place on the Venus surface and are communicated into the atmosphere efficiently because of the dense atmosphere and can be observed by balloons. So we don't have to be on the surface to do seismology on Venus. And the lower panel indicates the measurement of magnetic records. Venus has no magnetic field today, but like Mars and the Moon, it most likely did in the past. And those records are preserved as remnant magnetism, and a balloon at 50 kilometers is much better equipped to detect those than any other vehicle. And then finally, the ability to get below the clouds is vital to be able to see in the infrared the surface. Missions like Envision are going to be observing the infrared from above the clouds, but because of scattering, the resolution that it can do, the spatial resolution, is 100 kilometers. You heard that right, 100 kilometers. And that's inherent. It's not a limitation of Envision or Veritas's instrumentation. It's inherent to the scattering process. Get below the clouds, we can do 10,000 times better. Where do we go beyond this? A lot of science here. The message here is the future of Venus exploration for missions like a future sample return would involve buoyant vehicles, not retrieval with rotorcraft. And this illustrates work that was done in a study by the Keck Institute for Space Studies a couple of years ago, shows the evolution from missions we have today, the one I've just talked about, to systems that would acquire samples on the surface, float the samples up to altitude where they would be either analyzed in an orbit, in a laboratory, an aerial laboratory, or returned to Earth. So in summary, where are we with aerial exploration? Well, it's truly come of age, with aerial vehicles already deployed at Venus and Mars and flight at Titan planned for early next decade. For Mars and Titan, as I've said, rotorcraft will play a primary science role, but some potential for buoyant vehicles in the future. But for Venus, this is where the action is, destined to play a key role in all phases of exploration. It could do much better than orbital observations for surface measurements, the infrared. Landed missions are going to be limited in a lifetime, sophisticated landers. We don't have that limitation for a vehicle in the clouds at Earth-like temperatures. Rotorcraft cannot land to recharge batteries. We have the benefits of surface proximity. We can use the dense atmosphere to detect seismic measurements. And then finally, ultimately, looking decades ahead, surface sample science will require buoyant vehicles for raising samples from altitude from where they can be analyzed over months or longer or return to Earth. Finally, I'd like to thank the very many people who've contributed in this area. I'd like to recognize in particular Jacques Maman, who was a leader in this field. Jacques passed away about 3 years ago. And more recently, Victor Kazanovich, who led much of the work on the Vega mission and subsequently came to the United States and worked on many of these projects. Victor passed away last September. So thank you.